So algebraic expressions. So I think this is lesson 1.3. And we don't, in algebra, we don't like in math, we don't like long sentences or paragraphs. We like to condense everything into, variables, numbers, stuff like that. We can kind of condense it. And this is a lot of our stuff is based off linear thinking. What I mean by that, it's like you've heard of y equals mx plus b, kind of slope intercept form. You probably know that the slope is your m value, like your coefficient of x is your slope, and your b value is your y-intercept, so where it crosses the y-axis. You could also think of this, and it might help you in this these kinds of problems, think of this as the initial value. What I mean by initial value is if you have a graph, on that graph, it's going to cross the y-axis somewhere, and that's kind of like your initial value of your graph. Oftentimes, you're looking at that point on the y-axis as your initial starting point, and then you're increasing or decreasing from that point when it's talking about real world problems. So in this case, Sarah has $125 in the bank and plans to add to her allowance every week amount of $15. So the starting point, the initial value seems to be 125. So if I'm doing an mx plus b kind of problem here, I know the 125 is my starting value, my initial value. And then depending on how many weeks, that would be your coefficient or your slope in this case, your rate of change is 15. In fact, typically we're going to prefer to write this with meaningful variables, so I might try it like 15 w plus 125. So w is more meaningful because you probably already know w stands for weeks here in this case. So 15w plus 125 would be our expression for this sentence. And sometimes we have to evaluate, expressions or so forth here. So let's try to evaluate that. So it's really important when you do this that you substitute in with parentheses. And here's what I mean. So 4 times a squared minus 2 times b. So I would highly recommend use parentheses. And so when you plug in a value in there for -2 for a, I'm going to put -2 in the parentheses. I'm going to plug in 3 in the parentheses. And so now if you solve this one step at a time, this would be 4 times positive 4 minus 2 times 3 is 6. 4 times 4 is 16 minus 6. So the answer is definitely 10 right there. But it's very important that you put that negative, especially a negative. A is being squared, so -2 times -2 is a positive 4. Be very careful because a lot of students will type this in incorrectly into their calculator. So a lot of students will see this problem and they might try to use their calculator. So they'll say 4 times -2 squared minus 2 times 3 or something like that. And if they don't use parentheses properly, they'll get the wrong answer like that. So what you have to do is 4 times parentheses -2 squared minus 2 times 3. So using parentheses, you will get the correct answer because the first way I typed it there, the 2 is being squared, not the negative, and actually the negative is being squared and the 2, so -2 is being squared. This formula actually kind of might make sense with compound interest. It's kind of related. In this case, our p-value is kind of our initial starting point here. It's called a principal, how much you invest. R stands for the rate, always written as a decimal. T for time, always in years, and A is the total amount. So in this problem, it's just a matter of really, I guess, plugging into the formula. So we're going to plug into this formula. So A, well, we don't know that. A equals, the principal is 1,000 times 1 plus the rate is 0.1 or 0.1 to the power of T, which is 54. So we will simplify that. I think I might need a calculator for that one, so let's get the calculator out. So 1,000 times 1 plus 0.1 to the power of 54, and you get 171,872. 171,872. It's kind of amazing. So you started with $1,000, and 54 years later, you've got $171,000. So the power of compound interest is big there. The interest rate is very good. It's probably like a stock market or something like that. And simplify. Let's at least do this problem about simplifying here real quick. So simplifying this problem. So to do this, you really need the same denominator, right? So if I'm going to simplify this, I need to find a common denominator. So y squared over 8 plus, I'm going to leave a little room there, y over 3 minus y over 5, little space, plus y squared over 6. So you think about what's a common denominator. We need a least common multiple of 3. So a multiple of 3, multiple of 5, multiple of 6, and a multiple of 8. So you could do that a lot of different ways. 5 times 6 is 30. 30 is divisible by 3, but not divisible by 8. Maybe 60. Same with that. Is that divisible by 8? 64 is maybe 90. No, maybe 120. We could do this another way. Let me just show you. So you could say 2 to the third is the first one. The prime factorization is 3 to the first, 5 to the first, 6 to the first. If I multiply, I need all of these actually. So there's no repeats there. So whatever 3 times 5 times 6, that's 30 times 3 is 90, times 8 is 720. So I need this to be 720 is my denominator I need. So you would need to get your calculator out. So 720 divided by 8. Oops. 720 divided by 8. 720 divided by 3. 720 divided by 5. So this one's we're going to multiply by 90. So it'd be 90 over 720 plus, or sorry, 90y squared. So we multiplied this one basically by 90 over 90. And 720 divided by 3 is 240, so we're going to multiply by 240 over 240. So we get 240y over 720 minus, let's see, 144y over 720. And then finally 720 divided by 6 is 120, so plus, I guess, 120 y squared over 720. You're going to combine like terms like these two terms. Let's see. These two terms combine nicely. These two terms combine nicely because they both have the same type of y term there. So this will be 90 plus 120, 210 y squared over 720. And this would be plus, I guess, 96y over 720. And then you might be able to simplify that even further. Wow, why did I pick such a tough one here, right? So this is, right, I guess that'd be 105 y squared over 360. I think we could still take out a 5 there. So that'd be 21 y squared, 360 divided by 5, 72. So 72 divided by 72. Those are both divisible by 3. I think I could go even further here. So that would be 7y squared. 72 divided by 3 is 24 over 24. Wow. Plus. So this one, 96 over 720. So I know 96 divided by 2 is 48 over 360. So that would be, I guess, 24 out of 180. Wow, 12 over 90, 6 over 45. 6 over 45 is 2 over divided by 3 here, 2 over 15. Wow. So we have a y, I guess is that y squared or y there? It's just y, yeah. So these are all have a y attached. So I think we have 7y squared over 24, sorry, it looks weird, plus 2y over 15. So 7y squared plus 2y all over, oh no, we can't add those together. So you could keep those separate if you needed to. We could have put those together, I guess, here before we started simplifying each term. That would have been another way to go there. Let's just add those together there and then simplify that if possible. Let's talk about real numbers. So we did fill in this in class the other day a little bit. So real numbers, any number on the number line. So any number on the number line. So most numbers you've ever seen are real numbers. So I guess the exception would be, and we'll learn about these later, but there are such a thing as an imaginary number, and that causes from square root of a negative. So square root of negative 4, for example, or square root of negative 3 are imaginary numbers. But most numbers you've ever dealt with are real. So let's talk about decimals for rational numbers. So there are two things that have to be true with rational numbers. Either it's repeating, or the decimal is terminating. So these are pretty nice numbers. The decimal either stops or it repeats. So like 1.5 is a terminating decimal that stops at 0.5. Even the number 7.0, it stops. Repeating would be like 0.3 repeating. And that's a repeating decimal. So with either of these types, you can always write these as fractions. So you could write this as 1/3. That's a fraction of 1/3. You probably know that. If you put this as an improper fraction, this would be 3/2. So you can always write terminating or repeating decimals as a fraction. So another way to think about rational is you're really talking about fractions. Now, like even 7, like 7 can be written as 7/1. So a fraction of integers. Rational is the same idea as being a fraction. Irrational numbers, so let's talk about those. So the decimal for those would be kind of almost the opposite of this. These are either one of those, but this would be non-repeating and non-terminating. And that's an and, so both those are true. Think of a number like pi, right? Pi goes on and on forever. It doesn't ever stop, and it doesn't have any pattern to it. Square root of 2 is another example of an irrational number. So if you look at this big picture, all these numbers in the box, in the rectangle on the left, these are all real numbers. These are imaginary in this gray box. In the yellow, these would be called rational. And then the blue, this would be irrational. And a type of irrational number would be an integer. That doesn't have a decimal, right? An integer, like 1.5 is not an integer, but 1 is an integer, or -1 is an integer. So negative or positive numbers. Whole numbers are a type of integer. Those start counting at 0, so they're non-negative. So 0, 1, 2, 3, 4, 5. And natural or counting numbers start counting at 1. So whole numbers start counting at 0, whereas counting numbers start counting at 1. So let's look at a few examples of some numbers here and just put them in the proper spot. So like negative square root of 7, this would be irrational. This is a kind of a classic irrational number, which means that number is both irrational and real there. 2.35 sounds rational to me, but it's not an integer. It has a decimal. So it would be considered rational and real. That's still a real number, but it's not, it has a decimal, so it's not an integer. 0, let's think about 0 here. So 0 would be a whole number but it's also an integer. It's also rational. It's also real. Square root of a negative number is going to be imaginary. Square root of 121 is actually 11. Hopefully you know that. And so that's a counting number. It's which is also a type of whole number, type of integer, type of rational number.